In this video, we will prove one very important theorem that has already been discussed in Thomas calculus in previous chapter. So we want to prove this by using the approach different than the previous one. We use the approach of natural log. We take a natural log of x and we try to prove this from this perspective. So first of all, let me just prove. So let f of x is equal to natural log of x. We take a derivative, f dash x is equal to 1 over x. And when we put 1 over here, this becomes 1 over 1 and we get 1. Now apply the derivative, definition of derivative. F of f dash 1 will be equal to limit h approaches to 0, f of 1 plus h minus f of 1 divided by h. Limit h approaches to 0, f of 1 plus, or maybe we can change the limit x approaches to 0. Limit is the same, but we change the variable over here. 1 plus x minus f of 1 divided by x. We replaced h with x. Why did we change? We changed it since our function was natural log of x. So we replace this function with 1 plus x over here. Limit x approaches to 0, natural log of 1 plus x minus natural log of 1 divided by x. Limit x approaches to 0, 1 over x, natural log of 1 plus x, since natural log of 1 is 0. Okay, according to the definition, this power will be written as a power of natural log of. For natural log, this power becomes 1 over x. Now we apply the limit. We can take this limit inside of natural log. Limit x approaches to 0, 1 plus x, 1 over x. Since on the left hand side we have f dash 1 is equal to 1, so this is equal to 1 over here. So natural log of limit x approaches to 0, 1 plus x raised to power 1 over x is equal to 1. And when we take anti-log e raised to power natural log limit x approaches to 0, 1 plus x, 1 over x, e raised to power 1. This anti-log and log will cancel out, and the remaining term we have limit x approaches to 0, 1 plus x, 1 over x is equal to e. So that's how we prove this theorem by taking different perspective, that is of natural log of x, the definition of natural log of x, and some other properties. The next thing is we want to find the derivative of a raised to power x, a raised to power u. We know that a raised to power x can be written as e raised to power x natural log of a, as we proved earlier. We differentiate this function d by dx a raised to power x, d by dx e raised to power x natural log of a. Then apply the derivative on the right hand side. We have ex natural log of a. Since it is exponential function, it remains the same. Then we apply derivative on the power x natural log of a. So from here, we have natural log of a raised to power x, and the derivative of x natural log of a will be natural log of a, since x is variable over here. Exponential and natural log will be cancelled out, so we have ax natural log of a. So the derivative of ax will be equal to ax natural log of a. Okay. Similar is the case that the derivative of exponential function with base e will be equal to 1. So what about the integration? The integration of, first we just write a general form a of u natural log of a and the derivative of u if it is other than if it contains some other function in the power. And we also have a raised to power u du. The integration of au will be au natural log of a plus c. You can simply prove that by taking a derivative of this function. So this function is written as au natural log of a. Since natural log of a is just a constant, d by dx a raised to power u, 1 over natural log of a. The derivative of this function is au natural log of a. So we get a raised to power u, since this will be cancelled out. So we get the same integrand by taking a derivative on the right hand side, which is called an antiderivative of such function. Okay, so this was all about the derivative of au and integration, and we also prove this very important result in this lecture. Thank you for watching.